Okay. Okay. Thank you, Guangyang, for this kind invitation to speak at your online seminar, and also to the organizers for creating this series. So I'm going to talk a little bit about some non-MCMC work that Phyllis was kind enough to let me present here. And this is work that was led by Gerardo, my PhD student, together with Kevin Murphy at Queen Mary, and he graduated this year, and now he's a postdoc in Oxford. And I think he's in the audience here as well, right? So, okay. So I'm going to talk about one of the projects that came out of Gerardo's PhD, right? And this was a sort of an evolution of ideas of applying filtering to the problem of Bayesian online learning. Okay, so let's go ahead. Okay. All right, so let's go ahead and continue this. So the question that we were motivated by is the creation of agents that can somehow continually learn and adapt in their environment here. Okay, so these agents, from a technical point of view, they would, good agents. The desiderata for these agents is first of all to be able to learn continually from data sets that stream, right? And the second one would be to adapt to the data generating process once it undergoes changes, right? So these sort of are two things that adaptive agents should be able to do. Okay, and our goal is to address this from a Bayesian point of view, right? And relying on both the classical and the generalized Bayes frameworks, with the idea that we update beliefs as new evidence comes in, and that's of course with the use of Bayes rule. And the second thing is to how do you sort of address the second point, and the second point is addressed by adapting to regime changes, and we sort of rely on a hierarchical state space model framework in order to be able to do that. Okay. So, what's the motivation for this? Well, the motivation is actually quite sort of widespread, right? There's many different contexts, right, where learning and adaptation in non-stationary environments comes up. And it sort of comes up all across different applications in AI and machine learning. And some of the examples, some of the potential examples are listed below. So, contextual bandits, that's a bandit problem where you have external covariates that guide the choice of the arm that you're pulling. Test time adaptation. Then you have reinforcement learning. It can also be viewed from the point of view of learning in a non-stationary environment. Then you have a whole sort of subfield of modern AI, which is known as online continual learning. This is sort of the kind of learning where it's assumed that you never stop receiving a data stream, right? And you're always adapting to potential changes here. And the fifth one would be sort of general problems that come up in, again, different applications of ML throughout different domains, right? It's sort of known that covariance shift, prior probability shifts, and domain shifts are all sort of problems that can be encountered with an agent being exposed to a non-stationary environment. Okay. So, of course, this problem has been studied for a while, and various Bayesian methods have been proposed to tackle some of these problems. So, there hasn't really been a clear classification of these methods, and there hasn't really been, to date, right, a framework that's been built in order to somehow combine these methods together and possibly once we have an overall view of them, right, to develop new ones. Okay. So the purpose of this work was to unify, I said in the previous slide briefly, methods that perform Bayesian online learning in a variety of non-stationary environments, and by doing this, by creating this unifying framework, we're able to categorize the different methods and use a common sort of algorithmic language for all of them, right? So this would bring together methods that were developed in contexts such as machine learning, again, contextual bandits, continual learning and reinforcement learning, but also statistics where, of course, segmentation and switching state space models have been around for many years. And also, perhaps going back even further, right, to the engineering literature where system identification and filtering were sort of studied in non-stationary settings for quite a while as well. Okay. So Gerardo has come up with a nice implementation of this in JAX. It's a Python library, and it's available here if you want to try some of these methods out. Okay. All right. So of course, by having this unifying framework, right, we can also transfer methods from different fields, right? So if you have a method that's been developed in engineering for filtering, right, that method, once it's been sort of presented in this framework, it sort of simplifies its application to, let's say, statistics or machine learning, or sort of you can cross from any of these fields to any of the other ones. Okay. And the other motivation, beyond sort of a classification, right, is of course the development of new methods, right? So if we once we have the framework, right, we can almost see which sort of combinations of different choices of components of that framework have not been tried before, and thereby sort of perhaps be inspired by that to develop new methods this way. Okay. So let me now say the components of this framework that are sort of interchangeable or swappable in a way, and that define this framework. And the framework itself, you can think of it as being described by a state space model, and the different components of the state space model, they sort of determine how you handle this non-stationary environment that you're exposed to, right? That the agent, right, which utilizes this kind of learning paradigm is exposed to. Okay, so we start with defining a measurement model. Of course, this is a sort of a standard, right, in the state space framework, right? This is the model that translates some unobserved state together with some external covariates into unobserved measurement. So these observed measurement y's are assumed to come from the transformation of a state and the transformation of some external covariates. And then the second one, this is sort of perhaps less commonly explicitly separated, is this idea of choosing the algorithm to update the actual parameters theta, right? So the actual inference for these parameters, given the observed data, which includes these observations and these external covariates, it's also something that we can choose. So different methods are more suitable for different applications based on scalability requirements or so on and so forth. Then another thing we introduce here is this auxiliary variable psi, right? And the purpose of this psi is to track the different regimes that the data might be coming from. So this is what is used inside the state space model to track the non-stationarity in the process. So phi t, this psi t, is reflective of how sort of how the non-stationary in the data is sort of incorporated in our state space model here. Okay, so then the next component is a conditional prior, and this conditional prior is the way we sort of choose the belief for theta, right, before the data for the next step is observed. Of course there's different possible choices for this as well, and finally, our choice of an algorithm to assign different weights to different regimes, right? So this is sort of a way to decide on the plausibility of different possible psis, right? Because psi itself could take on multiple values, right? And we want to decide amongst all those possible values of psi which one is appropriate at a given time, right? And with which weights. Okay, so in online learning, this is more of an overview of the whole kind of structure of the problem. Is that we have a collection of targets, right? So these are some observed YTs. Their dimensionalities are RO, right? Just observation space, and we have some external features XT. So they're capital M dimensional here. Data comes in one data point at a time, let's assume that, and it's built incrementally over time starting at D1 and going up to DT. And the sort of one of the goals of online learning, one of the frequent goals of online learning is to estimate YT plus 1, so to forecast the response or the target at the next time step given the xt plus 1 and the data up to that point in time. So here we have all the x's and y's. Here we just have these external covariates, and here we have the yt plus 1. Of course, here the assumption is that xt plus 1, despite having the same index t plus 1, is actually available before yt plus 1. This is actually what we're trying to predict here. Okay. Okay, so let's now walk through the different choices of kind of components of this framework, right, and see how they can be combined together to build methods suitable for different types of non-stationary scenarios. Okay, so the first one is perhaps straightforward, right? This is more in a sense a review slide. So M1, modeling component 1, is the choice of measurement function. So if this is a probabilistic observation model that's driven by some latent state process and some external covariates, as I mentioned before, this could be any kind of probabilistic observation model with a conditional mean defined by some appropriate measurement function, right? So this would be linear regression. This would be logistic regression, where sigma is the standard sigmoidal function. Then this would be a standard one-layer neural network with ReLU activations. Or, of course, this can become arbitrarily complex, where H can be substituted by any neural network architecture that we want for this conditional mean model. Okay, so how would you estimate a posterior in this case? Again, a bit of a review. So if we start with the prior on our parameters of the observation model or the measurement model, and we have some data set, right? Sort of the static standard Bayesian approach is to compute this sort of batch posterior. And then once this batch posterior is computed, we can recursively update it by using the observation the next time step, right? Combining together with whatever our belief about the parameters is up to that time. Okay. So this is, again, perfectly standard Bayesian update rules, and this is how you can learn such a model online recursively as the data stream comes in. Okay. So there's also been a line of work in generalized Bayes, which I am sure some of the people in the audience are familiar with. And there, the idea is that sort of this observation model is presented in this way, right? So classical Bayes is a subset of generalized Bayes, where the choice of this script L function is the negative log probability, right? But this can be sort of a generalized choice of a loss function here that's sort of exponentiated and negated here like this, right? So this has been an area of some recent developments here. Okay. But the point is that this sort of the belief state about theta, given the data up to time t, can be represented, sort of with this model as well. Okay. So here's a diagram, right, of how this works, right? And this is a diagram which, again, some of you probably seen before. This is the diagram for a state space model, right? So we have the belief about theta evolving over time, right? And these y hats are the predictions that we make using theta, what we know about theta and the data up to that time, as well as some external covariates available at time t, right? So remember, so we have this, right? Okay, so I think this actually should be x3. Apologies. Okay. Okay. So now let's talk a little bit about one step ahead Bayesian prediction, right? Another thing you could do once you sort of have the model learning going. Right, so let's start again with this observation model, and this is the conditional measurement function, which we've seen before, and sort of given xt plus 1, we can do a bunch of predictions, right? So this is basically an elaboration on the previous slide, where there we shown the structure of the predictions over time, right? And here we actually look at how the predictions are done over time, right? So this is a computation of a posterior predictive mean, where y hat is computed as an expectation of this measurement function with respect to the posterior density that we have available to us up to that time. Okay. We can, of course, also do a map approximation if this integral is somehow difficult to evaluate. Certainly that's another possibility. And here we would just maximize p of theta given d of 1 up through t and plug that into the measurement function, and then that would be an estimate of y hat. Okay. We can also do posterior sampling, so we can draw, assuming we can draw samples of theta hat from the posterior, we can plug them into H, and then we can sample values of y hat by transforming sample values of theta and the given x through H. Okay. So now that we've outlined this, we can talk a little bit about the different choices that we might have for M1 and for A1 here. So question one is actually finding these recursive estimates. So for now, we've assumed that these recursive estimates are available to us when we're making a prediction, but we haven't actually talked much about how these are actually computed, right? And computation of these can be non-trivial, and closed form solutions for this problem are not tractable except in a small number of special cases. So one of these cases is of course the linear Gaussian case, where you have a Gaussian prior, and in this case you have a Gaussian posterior, and this kind of conjugacy lets you do closed form inference. Typically, this is not possible for models such as neural networks if you're trying to learn one online. And if you're doing that, then you must resort to some kind of an approximation. And resorting to this approximation in our framework is reflected in the choice of A1. Okay. So what are some examples of approximations that you could use when you're recursively updating a posterior? Well, a nice one that's been sort of, again, actively developed over the past 5, 6, 7 years is this idea of a recursive variational base. Here, your variational family is a Gaussian, and the nice thing about it is that it's specified only by its first 2 moments, and this problem is not that hard to solve online, right? So here, the choice of X here is this the generalized loss, right? So of course, as I said earlier, this could be replaced with a negative log probability of the observation model. So, but this is sort of something that's again a bit more general. So it's one possibility. Then we can have moment patch linear Gaussians, right? So this is also a classical approach, right, where the measurement function is linearized around the previous mean, right? So here's the linearization, and the model is a linear Gaussian model, and there the likelihood then is this normal with h bar as the mean, and RT is the moment patch variance of your observation process. So because of this, linear Gaussianity of the likelihood and the Gaussianity of the prior updates become quite straightforward, right? So this now becomes our posterior, right? Once we observed data time t, and from this posterior we can easily get the one step ahead forecast because we know exactly what h is for this approximation. Okay. So here's a nice sort of example, right? This is online classification of neural networks. Again, credit to Gerardo for these nice animations. So here we're interested in doing online Bayesian learning So this is what we're doing. A1, right? M1, and we want to do this using a two hidden layer neural network. That's the choice of observation model, and we want the computation to be done using moment matched linear Gaussians, right? So what I described in the previous slide. And here, data is only seen once, and what we want to do is we want to sort of we want to classify points coming from either the black dots or the white dots class into the correct class, and this of course entails learning a decision boundary. Okay, and we can evaluate the exponentially weighted moving average of the accuracy in the one step ahead forecast. So this example we'll come back to, but this is sort of the points from the white class. These are the points from this is the black class, and our goal is to learn some kind of decision boundary between them online, assuming that you observe the points as they come in and you see all of the points only once. Okay. So here is our measurement model. This is a two-layer hidden layer neural network, and this is quite standard, right? So this is a way of defining it in JAX here. So basically, JAX allows you to define a network by specifying a sequence of layers that transform the layer that is preceding them, right? So we start with the dense, then we have a rel, another dense, right? So we have this kind of structure. This is standard way to program such a neural network in JAX, right? So here's the first layer, and this is the second layer, roughly speaking. Okay, and then the output is a classification model. So this is the Bernoulli probability. Okay, so the way that this is actually done, if we walk through all the steps of the posterior computation and the moment matched linear Gaussian for this neural network model, we have to basically compute a few things here, right? Including the Jacobian, the one step ahead prediction, the moment matched variance. So there we go. That's the RT that I referred to in the previous couple of slides ago. And then these are standard Kalman filter computations. And then once these are computed, right, we can update the posterior as such, right? So this is a nice way of doing this with kind of Kalman filter computations. Okay, so let's go on with this. So here's
Sorry, can I ask
please. Of course.
Clarifying question. How are you also training the neural network online?
This is still training the neural network online. Exactly. Yeah.
Okay,
So
every step you train the neural network first, and then you update the posterior using this.
Every step you update the posterior basically using using this, right? So one data point comes in, you update the posterior. Another data point comes in, you do another update to the posterior. So this is literally one data point at a time updates.
And the neural network parameter is also updated every time you have a new data.
Exactly. Yeah. They're updating using this filter every time a new data point comes in.
Okay.
So this is like learning as filtering, right? So you pretend the parameters of the net are the state of a model, and then you update them using this kind of Kalman filter as data comes in one at a time.
But is the entire neural network retrained every time?
Well, I mean, not retrained per se. It's the posterior of the neural network's parameters is updated every time a new data point comes in. So every time a new data point is observed, we perform these computations, and then the P of theta t gets updated with this new data point incorporated into the parameters. I will go on. Thank you for the questions. Okay, so here's basically how it looks if we do a single pass of the data, right? And this so again, animation by as I mentioned by Gerardo shows that as you observe more points, this is the exactly same data set that we looked at previously. You see how this learning is happening, and this is how the accuracy is tracked. So bit by bit, this decision boundary stabilizes. But when we start, of course, this boundary is quite far from where it eventually ends up. But every time a new data point is observed, the parameters of the network are adjusted, and therefore this boundary changes. Okay. But of course, this is a nice scenario. This is a nice example because here there's no non-stationarity, and indeed, you don't have any kind of rotations, for example, right, of the classes, and therefore the boundary learning stabilizes over time, and the accuracy sort of is not is not dipping at any point, for instance. Okay. So now let's go to the non-stationary bit. We sort of for now looked at how learning can be done online. We looked at a simple example of how learning can be done online successfully using this linear Gaussian approximation for a classifier problem. But now, and this is more to the point of the talk, what happens and what do we have to overcome when there are actual changes in the data generating process? Well, if we have if our model is misspecified and sort of our model lacks capacity to adapt to data that comes from a misspecified model, then we're going to have a decrease in performance. And in this case, more data actually does not necessarily mean your performance will be better, implying that you have to have some kind of a more drastic adaptation strategy in your model than simply feeding more data to it and hoping that it's going to somehow adapt and adjust to your data stream. Okay, so this is sort of a relatively classic example of non-stationary data. This is the rotating version of this two moons data set. This is known in the machine learning literature as the two moons data set because you have one moon and the other moon, and the goal is to learn this kind of squiggly boundary that separates them. Right. So here, the DGP, the data generating process, is forced to change every 200 steps. So we can see how it's rotating basically, right? So from time 0 to 200, this black moon is down, right? But from 600 to 800, this is completely flipped, right? So boundary that would, if it passes through here, right? Well, it would be completely wrong, right? If you learned it on this part of the data alone. So if the agent's not aware of these change points, then we can reasonably expect some kind of failure to start happening here, something basically to go wrong. Okay. So the full data set, if we don't know what the task boundaries are, this is basically what happens if you superimpose everything in this slide on top of one another. Looks like this. Okay, there we go. So let's look at how the accuracy of these updates, sort of what happens if we have a neural network attempt to learn this classifier, right? And what we see is that it performs fine on the first block of data. It performs reasonably well in the second block of data. It still performs reasonably well in the third block of data, but by the fourth and fifth blocks, when the rotation has been completed, you see that the method essentially begins to fail, right? And in the continual learning literature, and borrowing this term from there, this is known as the lack of plasticity, right? Lack of plasticity basically means that you're fixed in your ways and you cannot adapt further, no matter what sort of data comes in. You're just not capable of sort of processing things. And you sort of go back to 0.5, which is basically a coin flip classification, which is number one. Okay, so this example, at least in some sense, suggests that just being Bayesian and feeding more data in is not enough to sometimes overcome the encountering of a non-stationary data stream. So you do adapt to some extent. We saw some adaptation happening, but this adaptation is not sufficient, even in this scenario, right? And this sort of is a motivation behind the field of continual learning. And there the assumption is that the data arrives continuously; it never stops arriving. But of course, this is the methods there attempt to address this kind of adaptivity beyond what is given by standard Bayesian inference, right? Rather building on it. Okay, so pausing for a second, we say that approximating the posterior and choosing the measurement model should be viewed separately from the adaptation strategy that we use. And so on one hand, we have the approximation, and that's fairly sort of fairly clear. And on the other hand, we have the measurement model, which is also fairly clear. But the actual adaptation strategy of fitting this posterior and this measurement model to this non-stationary data stream is something that should be considered separately, or arguably. Okay. So how do we do this in a Bayesian way? And if you recall, a number of slides ago, I mentioned this auxiliary variable. I mentioned this auxiliary variable psi, right? And this auxiliary variable psi is what's going to be inside the state space model. It's going to be the component of the state space model that we're going to use to track and to adapt to the non-stationary that we encounter, right? And this is specified in our framework as M2 and M3, because of course specifying the auxiliary variable is not enough by itself, but also we have to say what the effect of this auxiliary variable is on the prior, right? How does the auxiliary variable affect the prior on the parameters that we're trying to learn before new data is observed and before this new data is used to update the parameters at the next time step. Okay. And we also have a choice of a posterior over different auxiliary variables. So this is the question of how do you feed back information from the observed data into what you know about the auxiliary variables. Okay. So we have that, right? So this is a little taxonomical classification, right, of the different ways that people have used auxiliary variables before, sort of perhaps sometimes very explicitly, right? Sometimes slightly more implicitly to adapt to non-stationarity. So again, as I said, this is a framework, right? Therefore, we look at existing methods and we sort of try to understand how these methods can be represented in a framework. And the auxiliary variable seems to be a recurring theme in them, and so this becomes something that we choose, right? So I'll sort of highlight one example. A discrete auxiliary variable to track non-stationarity can be used to drive an adaptation strategy of simple resetting of the prior. So this arrow here from discrete auxiliary variable to this box, which is abrupt with reset, includes methods such as the sort of the Bayesian nline changepoint detection method, where this variable upon being inferred drives us to decide whether to forget everything we've learned before and start learning from a new data set from scratch, because that's actually potentially advantageous, because whatever we learned before might be completely irrelevant for the data stream that we're encountering now. So this would be this kind of adaptation strategy. There's of course softer ways of doing things. So another work this is one of our works from before, and we can assume that there's a constant change in the data, but this is sort of a softer adaptation, right? We don't explicitly forget everything and then sort of completely throw away everything we learned up to now, but we adapt bit by bit over time, right? So the parameters have some noise added to them bit by bit over time, and the addition of this noise increases the plasticity of the model, and then this allows us to adapt to new data streams. Okay. And basically, in our framework, M2 and M3 can describe a large collection of existing methods, and which describe how non-stationary has been addressed before. Okay. All right. So now, talking about non-stationary, let's make this a bit more explicit, and let's talk about the choice of the auxiliary variable psi, right? So one possible choice is inherited from the change point detection literature. And in change point detection literature, you typically track something like a run length. So the run length is a variable that tracks the time since the last change point. Okay, so here we can set our variable psi to be RT. RT is the number of times since the last change point, right? So here we're tracking. This is a change point, so we reset RT, tracking, reset it again, RT. So here we have two change points that occurred, and we sort of do something to the prior at this point, right? So for example, this could be the point at which a prior is completely reset, and we forget everything we've learned up to now because something in the data is telling us that there should be a change in its structure. Okay, so this is another variation on this idea, except here we also count the number of change points that have occurred. So this is an indirect way of keeping track of the rate at which the change points occur over time. Okay, we can also encode change point locations by using, for example, this binary sequence, and this encodes even more information. We can encode the number of time steps since the last change point. We can encode the number of change points, the count, and we can encode their location, so through these binary strings. This is another choice of a latent variable psi to track the non-stationarity. In this case, psi has a growing dimensionality, and it sort of behaves this way. Okay. And further on, and so on, so on and so forth, right? Another way is sort of a tracking with change point probability. This is sort of a softer version of what we've seen on the previous slides, and here we compute or track the probability of a change point happening at a given time, right? So here it's 1 because the change point actually occurs. Okay. Mixture of experts can also be thought of as fitting into this framework of adaptation to non-stationarity. Here, we can choose amongst different models. So here we're using model 3, right? Here we're switching to model 2. Here we're switching to model 1, right? So mixture. So you can think of adapting to non-stationary stream by picking different models that handle different aspects of the non-stationarity that you're encountering. It's possible too. Okay, and I mean the sort of most trivial choice would just be to have a single choice of model throughout. We include this for consistency of the framework. Okay, so here's some auxiliary variables. I haven't covered all of them in the past slides, but these are covered in our paper, and these are the different things that we found in the literature that have been used to track non-stationary over time. Okay, so we can see some of them are trivial, some of them have a fixed dimensionality. So, like, for example, this, right, RT. Some of them have growing dimensionality, like for example, CPL and so on. Okay. So next we go to the choice of conditional prior, and the conditional prior is what this psi-t modulates, influences, controls over time, right? So this part tracks our non-stationarity, but of course, what we want to do is we want to somehow have this track the non-stationarity influence the choice of our prior over time, right? In other words, for example, forgetting what we learned up to now. Okay, so there we go. We feed in our choice of psi into M3, which is where the past information that we know up to now is stored, right? So M3 is a bit more of a relaxed definition. It doesn't necessarily have to be the posterior at time t. It's a conditional prior. We're somewhat flexible in defining it, and this conditional prior is influenced as well by our choice of psi-t. So we have a conditional prior, which depends on the data observed up to time t-1. It also is somehow modulated by whatever the choice of psi is. And of course, we have our current information in this generalized fashion coming into our model as well. So for example, let's sort of zoom in a little bit on the Gaussian case of choosing the conditional prior. And here we have so here's our normal model, right? This is the conditional prior here, and here we're flexible in choosing the mean vector and the covariance vector, and having them depend on psi in both cases. Okay, so of course, if we choose psi-t to be just a constant, a dummy variable, then this just becomes the classical Bayesian update, right? Again, included here for completeness of the framework. We can have a run length with prior reset, and this is that first branch that I pointed out, where we use Adams and Mackay's Bayesian online change point detection algorithm, which is dependent on tracking the run length. But now, in our case, the run length now determines whether we decide to change what our prior is, right? So here we can see that the moment that the run length is reset back to 0, we choose mu0 and sigma 0 as our prior parameter. So this is explicitly saying that let's forget everything that we learned up to now upon the encountering of a change point. Right? So that's the logic here, right? And until a change point is encountered, right, we'll keep learning. Yeah, we'll keep learning. Right. Similarly, we can sort of forget things, but we can forget things in a much softer way, right? So if we track the change point probability, then of course we don't have to sort of do a hard forgetting. We can do a softer forgetting, and this is just a reflection of that, right? We take this combination of the prior mean and the currently learned mean, and likewise for the covariance. But of course, here, if the probability of a change point is close to if mu t is close to 0, then we set this to be mu0. If likewise for the covariance. Okay, so there we go. Okay, this is a bit more of how we can use the change point location to decide which data set from the past we pay attention to. So this is this kind of growing choice of psi-t, and here the idea is to modify the index set that's used for tracking the mu and the sigma. Okay, this is sort of analogous to the method that we used in Chang work that I pointed out, where we have covariance inflation over time. So this is sort of another simple way of adding in a little bit of noise to the covariance over time, and by adding a bit of noise to the covariance over time, you're enabling some forgetting to happen, and therefore you're enabling some learning to happen once new data is observed, which can potentially come from a non-stationary data stream. Okay, so here's how we can predict things, right? We have to condition on psi and the given data, right? So this is just combining together what we saw in the previous few slides, right, into prediction, into concrete prediction. Okay. Finally, we come to choosing how we put probabilities over the psi's themselves, and basically we can recursively update the psi's as we would in a layer of state space model in this fashion. Okay. We can also choose right. We can also choose the weights for the different psi's using this loss-based approach, and this would again give us weights for different regimes, right? The reason I'm using alpha here, the reason we're using alpha here is that this is sort of kind of connecting into the mixture of experts approach, right? Where we used alpha to pick the model, to track the model that we're using at a given time. Okay. This I believe came from some work by people at DeepMind who used this kind of empirical Bayes estimate in order to do learning with non-stationary data streams, and if viewed within our framework, it becomes something like this. Okay, so finally, this is the algorithm. It's called acronym BONE, Bayesian online learning in non-stationary environments, and now we've looked at all the possible choices of so what's happening here in this framework. Okay, so I think I have a couple more minutes. This is just a few definitions of what's possible with BONE, and this is one of the kind of the conceptual way of making a prediction, right? So basically here we're adding this additional bit where we are averaging over the different psi's, where the weight function is chosen by our choice of A2, right? And our Q, our posterior, is updated using this choice of conditional prior, as well as the given observation model. Okay. So if we come back to our non-stationary moons example and apply BONE to it to see how it can handle changes over time with different choices of combinations of M2, M3, and A2, we can look at this as follows, right? So here we go. Right now we can sort of see that resetting back to initial weights actually works pretty well because there's enough data in each block that learning, starting to learn from scratch, is acceptable. We can quickly figure out what a new boundary is, and it's okay to forget it before switching to a new data stream. Okay. Again, this is working sort of reasonably well, perhaps not as good as the previous one. If you constantly forget past information.
Next question.
Please.
It seems like you have another boundary coming into play, like on the outside, on the periphery. Why does that happen?
Because the forgetting is not happening fast enough, so to speak.
Okay.
Right, like if you look at this one, right, you see that you see here, like you completely forget things, right, and you learn you learn the boundary from scratch. Like here's a relatively simple boundary, right? You see that once forgetting happens, you revert back to learning a boundary starting from the very simplest possible one. So this one, the resetting is of course not complete, right? Because here you're still picking up information from the old weights, which is sort of analogous to the initial failure mode that I exhibited, right? This is like a softer version of that. Now, as I mentioned earlier, Bone can also be used to create new methods, and by combining different choices inside the framework. For example, we can combine gradual and abrupt changes, a somewhat natural thing to do. So we can do this. We can combine soft and sort of soft and hard resets here. Basically, we reset if the probability of a change point is below some threshold. Okay, and these are weights for the different choices of the auxiliary variable psi. Here it's a run length, so it's r. Okay, and we can do this here, right? And the point is that this method works fairly well, and it gives us essentially state-of-the-art performance on this and other tasks. Okay. If we optimize the hyperparameters, we see that we can do fairly well with our introduced RLO UPR method, right? So this works. And here's a big table, which is again in our paper. Basically, it takes a bunch of methods dating back to the 1960s, right, and attempts to classify them all by the different choices of components inside the framework. Okay, and finally, a real-world experiment on predicting electricity load. I believe from a large European city where the interesting thing happens around COVID days, where electricity usage, the pattern of electricity usage changes quite drastically, right? And this is what happens during normal times. If we see this cyclical pattern, right? Electricity demand has this cyclical pattern, as you might expect it to have. And here's what happens around March 7th, right? So this is probably when some COVID restrictions kicked in this city. And we can do forecasts here, and basically,
Patrick, I'm one of the grad students. I don't think you've met before.
Oh, no, I haven't.
Oh, nice to meet you.
Oh, Phyllis. And here we can see that basically, we have these relatively frequent change points up until now, but something happens here, and here this becomes quite different, right? And so the forecast has to change, right? Here we see this illustrates that our choice of method works reasonably well for this forecasting problem. And I think I am out of time, but there's more examples available in the paper, right? And again, this work was led by my Kevin students Gerardo, and credits for the animations and the slides to him. So I will stop here, and this is our paper, which is now actually in TMLR, right? So that link is out there, but that archive link is also linking to the current paper as well. So I'll stop here, and thank you again for this. Thank you.